now I would like to solve this. Okay. So, what I have is this, now I would like to solve this. So, we can either obtain a solution of this equation, right. It depends on at what level you want to solve the problem. Okay. Either I can simplify and I can take some specific cases, or I can solve it for a very general case. What I am trying to say is that I can solve this, I can simplify this equation and obtain a much simpler differential equation which I can solve if I assume that I am working with low potentials. Okay. Or I can take a case where I am working with Z is to Z electrolyte. Okay. Z is to Z electrolyte, that means I am working with symmetric electrolyte. Okay. Z is to Z, for example, NaCl is an example of a symmetric electrolyte, that is Z is to Z, right, 1:1 electrolyte, right. So, for cases like that, I think you can solve this expression fairly simply, but if you look at very complicated cases where the potential is very high, or when you are working with non-symmetric electrolyte, this so the solution is much more involved. So, we will take a simple case of low potential. Okay. We will come back a little bit and then tell you what that low potential is, but for the sake of simple, what we will do is, so I have this expression. Okay, let me write that up. So, this is d square psi by dx square, right, is equal to minus E by epsilon sigma Ni infinity into Zi exponent minus Zi E psi divided by kBt, right. That is what we had derived, right. So, now, so when I say if you look at the right hand side, right, when I say it is a low potential, this rho star we were expressing it as summation of I for all the species Zi times E Ni, right, and the Ni infinity we used to represent it in the form of Boltzmann factor, right, and Boltzmann factor had this exponent minus Zi E psi divided by kBt term. Okay. So, the moment I say low potential, I can take an exponential term. Okay. For a low potential, I can write this as 1 minus Zi E psi divided by kBt. Okay. So, that means if you have a e power minus 6, for example, okay, we know that I can write it as 1 minus x plus x square by 2, right, that is a series, right. I can kind of omit all the higher order terms. Okay. I can restrict only to the first terms. Therefore, I can actually write e power minus x as 1 minus x. Therefore, this exponent minus of Zi E psi by kBt, I am writing it as 1 minus Zi E psi divided by kBt. Is that okay? Yeah.
Already one negative sign also.
No. So, if you look at this, right, so I am only talking about this term.
That will give you 1 minus Zi
Yeah.
psi by kBt.
Correct. Yeah.
But coming below.
Yeah, that is it. I have only have. So, I have. So, this is.
Oh, okay.
Yeah.
Only rho star.
Yeah. I am only talking about the rho star. Okay. I have only rho star. Rho star we wrote it as sigma of I Zi E Ni. Okay. Ni infinity I am supposed to write in terms of the Boltzmann factor. Okay. And there is an exponent minus Zi E psi by kBt term. Okay. I am going to write that as 1 minus Zi E psi divided by kBt. That is all we have done. Okay. So, therefore, I can simplify this as sigma Zi E Ni infinity times 1, that is this term, okay, multiplied by minus sigma Zi E Ni infinity and the next term, okay, Zi E psi divided by kBt. Okay. Now, if you look at this term, right, what can you say about this term? So, this is, what is it? Yeah, so in a way it's rho star infinity, right? In a way it's rho star infinity, and rho star infinity is actually 0, right? Because if I look at a, so what you should imagine is this, right? Whenever I talk about a distribution of ions in solution, okay, so imagine that I have a electrolyte solution, okay, Na plus and Cl minus. So we know that at equilibrium there will be some distribution of ions in solution, okay, right, and there is a, because it is a symmetric electrolyte, there is an equal probability of finding Na plus and Cl minus everywhere in the solution, right, if you have a homogeneous solution. Now what I do is I bring in a charge species now, okay, whatever distribution that I had earlier is going to be disturbed, right. There is going to be lot of restructuring of ions, and the restructuring of ions will essentially lead to a electrical double layer formation, right. That means the concentration of counter ions close to the charged surface is going to be higher, but if I go to a sufficiently far away distance, okay, then you will have again the distribution of ions is going to be very similar. Okay, I am talking about one plate, for example. I am talking about when I say infinite distance, that means it is sufficiently far away from the charged surface, and you will learn a little bit later, when I say sufficiently far away distance, we are talking about a distance called the thickness of the double layer. That means if you go to a distance which is farther than the double layer thickness, you know, there will be equal probability of finding the positive ions and negative ions in solution. Okay. In such a case, this rho star infinity is going to be 0, because if I am working with a, like say a simple case of, you know, Na plus and Cl minus, this term is going to be plus 1 E Ni infinity minus 1 because of the Cl minus E Ni infinity, because if I add 1 millimolar NaCl solution, I am actually adding the same concentration of Na plus and same concentration of Cl minus ions, right. Therefore, yeah,
This is applicable only for Z is to Z.
this is, yeah, this is, no, it will also, even otherwise, no, I am only talking about, only thing is if I take for example CaCl2, okay, is going to be plus 2 times for there will be 2 times minus 1, right. So essentially this is applicable irrespective of you know, on an average the total charge there is 0, okay. Therefore the total potential will be 0 at you know, right. Is that okay? So therefore the first term becomes 0, therefore this term becomes 0. I am only left with the second term, okay. Therefore I have Zi here, another Zi there, therefore there is a Zi square that comes in, okay, and you have E, therefore you have E square, and there is psi, okay, divided by kBt, okay. So which I can express it as, okay, so there is a minus there, right. So because I had, so there is a rho star, right. So this is rho star, and because I had d square psi by dx square is equal to minus rho star divided by epsilon, okay. There is a minus gets cancelled, therefore I am left with, okay, and of course another epsilon comes in because I had a epsilon in the denominator. So therefore d square psi by dx square is equal to E square, okay, divided by kBt and epsilon, okay, and summation of all the ions in the solution sigma I Ni infinity into Zi square multiplied by psi. Is that okay? Now let us think a little bit about what is this, you know, we said that, okay, so this expression, right, I said this is a Poisson-Boltzmann equation, right. Now this expression is what is called a linearized Poisson-Boltzmann equation, which is applicable only for the case of low potential, okay. What do I mean by low potential? ZIE times psi must be much less than kBt. Okay. So, now you can put in some appropriate numbers. So, let us for a okay, let us say that so let us look at the limiting case. Okay, ZIE psi okay, must be less than kBt for me to assume for me to say that I am working with a low potential case, right. So, if I take E psi is equal to kBt, okay, that means I am talking about again if Zi is equal to 1, okay, therefore, E times psi is equal to kBt. I know what is kBt, right, the thermal energy. So, 1.3 10 power minus 23 joules per Kelvin multiplied if I am working with 298 Kelvin, and E is the charge in the electron. The psi comes out to be something like 25.7 millivolts. Okay. So, you can say that if you are working with charged particles, at 298 Kelvin at room temperature, okay, if the potential, okay, if the zeta potential of the particle that you have measured, if that potential is 25.7 or lower, I can assume that the particle charge is low. Okay. So, that is so you can kind of get an estimate as to what do I mean by a low potential or high potential by this simple approximation. Okay. So, this psi, if you work with if I work at 25 degree centigrade, if you a potential can be regarded as either low or high, okay, depending upon whether the charge surface that you are working with has a potential that is less than 25 millivolts or more than 25 millivolts. Okay. This number is important because sometimes you may be working with, like, say, a charge stabilized dispersions, okay, say that it is charged, okay, positively charged particles. Okay. You and somebody measures the charge on the particles and they say that it is 15 millivolts, okay, or somebody works with the a case where the charge is, say, minus 100 millivolts. Okay. So, we know that definitely a higher charge means is more stable, but however, if you look at this the case even in the case where the charge is 15 millivolts, okay, or the surface potential is 15 millivolts, there would still be electrostatic repulsion. Okay. However, it may not be sufficient, right, to for the particles to be stable. Okay. So, of course, the more closer to 0 it is, that means that your charge interactions may not be very important at all, right. So, therefore, you can keep this 25 millivolts in mind, okay, that if the surface charge is such that the surface potential is 25 millivolts or lower, such systems exhibit very limited stability because of the electrostatic effects. Okay. Okay. So, now you have this linearized Poisson-Boltzmann equation, okay, and of course, if I so this this quantity, this is a quantity of which you have control over, right. That means some of them are constants in the equation. So, E square is constant, epsilon is related to the medium in which the particles are dispersed. So, you will typically know those values, and of course, kBt is the thermal energy, and if you work with finite temperature, and of course, you have control over the concentration of the ions that are in solution, and also you will know their valency, everything. Therefore, I can plug all these constant together into and say it is kappa square. Okay, it is kappa square times psi. Okay, therefore, d square psi by dx square becomes kappa square into psi. Okay, that is your linearized Poisson-Boltzmann equation, and of course, I can solve this, right. So, you have, if I use the boundary conditions that at for as x tends to 0, psi becomes psi naught, and as x tends to infinity, psi becomes 0, right. If I use these boundary conditions, so it turns out that psi becomes, psi goes as psi naught into exponent minus k times x. Okay. You know how to do this, right. So, you will have psi, you can write it as a times e power exponent of minus k x plus b times exponent plus k x, right. That is the solution. Okay. And if I substitute the boundary conditions, you will essentially get this. Okay. So, that is the solution for Poisson equation, okay, in one dimension. So, essentially what this tells you is that if I have a charged surface, okay, with some counter ions in solution, okay, so the potential essentially decays as an exponential function. Okay. So, now I with this, given if I know what is kappa, I will be able to calculate what is the potential at every location, right. Okay. How does that vary as a function of separation distance, and I should be able to calculate that, given that I know what is psi naught and what is kappa. If I know that, I can know what is the variation of potential with distance. That is what we were after.
It is not kappa square, it is only.
No, it is kappa. Okay. Psi is equal to psi naught exponent minus k times x. Okay. You can work it out. Okay. Yeah. Right. You can write this as d square psi is equal to kappa square psi, d square minus k square is equal to psi is equal to 0, right. So, you can you can do that out. Yeah. So, what we have done is a case where we are trying to think about a potential distribution near a planar surface, right. You can, and this particular assumption, okay, that low potential, it is what is called as a Debye-Huckel approximation. Okay. So, what is called as a Debye-Huckel approximation, and Debye and Huckel are the two people who developed solution for the Poisson linearized Poisson-Boltzmann equation, which is applicable for low potential cases. That is why this particular solution that we are looking at is what is called as a Debye-Huckel approximation, right. You can do a similar calculation for planar other kind of geometries as well. Okay. Instead of spherical, instead of a planar surface, if I am working with spherical surfaces, I can again do a similar kind of a formulation, and only thing I have to do is I am going to consider again, if you look at the spherical coordinate system, right. I am again going to assume that psi is a function of only r. Okay. It only varies as a function of r, is only a function of r. Therefore, I only take the only the first term, that is 1 over r square d by dr of r square into d psi by r. Okay. That is the first term in the general expression, in the general Poisson equation, okay, because I am only worried about how does psi vary with r. Okay. That is the first term, and again I can the right hand side, okay, again I am going to linearize it. Okay. Therefore, I essentially end up with again a linearized Poisson-Boltzmann equation in the cylindrical, in the spherical coordinate system. Okay. So, that is going to be the starting point, and I can of course solve this as well. Okay. It is a fairly simple derivation, so you should be able to work it out. Okay. So, what we will do is in the next lecture we will try and solve Poisson-Boltzmann equation for the spherical surfaces case, and then we will talk a little bit about what is the importance of this kappa square. Okay. Because this quantity is very important, because in any calculations where you want to extract the electrical double layer interactions, you should know how to calculate that. Okay. And we will talk a little bit about what is the importance of and how does it depend on the salt concentration, how does it vary. Okay. We will discuss some of those things in the next lecture. Yeah. Thanks.